Welcome to AI Paper Slop. If you're an ML engineer or researcher, you know the drill. We pull the most important AI papers and just completely tear into them. And today, we have an absolute monster of a paper.
Yeah, this one is, it's genuinely a paradigm shift.
It really is. It's called Hydra-0 Action Flow for Generalist World Modeling and Control. It's from this massive collaboration, NVIDIA, Brown, Columbia, Harvard, and look, I want to give you the core insight right out of the gate so you know exactly why you should care about this.
Right. Cut straight to the good stuff.
Exactly. So Hydra-0 essentially solves the multi-embodiment bottleneck in robotic world models. Historically, if you're training a video model for robotics, you condition it on robot-specific joint angles, which, as we know, is an absolute nightmare for generalization.
It's the worst.
Right. But Hydra-0 just throws that completely out the window. They introduce this thing called action flow. They represent robot actions purely as two-dimensional pixel motion.
Which sounds so simple when you say it out loud, but
Yeah. But the implications are insane. By using this shared visual interface, a single world model can learn from human hands, a single-arm robot, complex bimanual setups like all simultaneously.
yeah, and the results speak for themselves. They saw a 90.4% drop in robot motion error.
90%.
Yeah, and the real kicker is that this model functions as both a forward simulator and an inverse controller. So it's capable of zero-shot real robot control.
Which is just, that's the holy grail, right? To get to zero shot on physical hardware. So let's unpack this. Imagine trying to teach a human being how to play the piano, right? But instead of sitting them down and showing them how to move their hands, you hand them a giant spreadsheet of joint torque angles and muscle activation values.
Right, like here's the exact rotational force you need in your pinky finger.
Exactly. They would fail completely. It makes no intuitive sense. But for years, this is exactly how we've been trying to train robotic world models.
It's been the historical bane of existence for anyone in physical AI. If you're training a generalist world model, your entire goal is to leverage every single scrap of data you can find.
Yeah, you want internet-scale data.
Right. You want it learning from UMI grippers, right. But a UR5 robotic arm is going to move its physical joints in a completely different sequence than a Franca arm just to reach that exact same point in 3D space.
So the visual output, the video of the arm moving, looks pretty similar.
Right, but the underlying numbers, the joint torques, are completely foreign to each other. So the video generation model, which is just trying to predict the future, is looking at a numerical disaster.
It's forced to learn this crazy embodiment-dependent mapping from a raw command to visual dynamics.
Yeah, it essentially has to memorize the physical hardware structure of every single robot in the data set just to figure out what the pixels are going to do next.
I always think of it like trying to open a proprietary file format. Sending joint space commands to a generalist video model is like sending a file that only one specific brand of robot hardware can even read.
That's a perfect analogy, actually. It's useless for a general model that just wants to understand the underlying physics.
Which is why we need a universal language. And that brings us to the core of the paper, action flow.
Right, action flow. Instead of that giant spreadsheet of joint angles, they feed the model a set of camera plane trajectories. It describes the commanded motion of the visible robot embodiment.
They're literally mapping the mechanical command directly into pixel motion on the screen.
Exactly.
Okay, but as an engineer, the second I hear that, my immediate question is how do we actually build this without hallucinating the physics? Because video models love to hallucinate.
Oh, they do. And the researchers split this into two distinct construction modes. There's deployment, so the forward mode when you have a real robot.
Mm-hmm.
And then there's offline training, where you might just have raw internet video.
Let's start with deployment. How does it work when I actually have geometric data and a physical robot?
So at deployment, it's a geometry-aware setup. You have a candidate command you want to execute.
Yeah.
But instead of passing that raw number straight into the video model, they first send it through the robot controller and a full physics simulation environment.
And they used Isaac Lab for this architecture, right?
Yep, Isaac Lab.
Okay, wait, I have to push back here. When I read that, red flags went off regarding latency.
The compute overhead.
Yes. We're running a full physics rollout in an Isaac Lab simulator at deployment just to generate a 2D visual condition for the video model. In real-time robotics, every single millisecond matters. Doesn't this introduce a massive compute bottleneck right at inference?
It definitely sounds computationally heavy on paper, I'll give you that. But it's actually the crucial grounding step that makes the whole system viable.
Because it forces the physics to be real.
Exactly. That Isaac Lab rollout grounds the 2D condition into something kinematically executable. You aren't just letting a generative video model hallucinate how an arm might look if it moved to the right.
Right, you're forcing it to strictly obey the physical laws of that specific robot's joints.
Yes, it perfectly bridges that gap between generating pretty realistic pixels and adhering to actual hard physical mechanics.
Okay, I see the distinction. So the VO model doesn't have to learn the complex kinematics because Isaac Lab just handles the physics constraints up front.
Right, so Isaac Lab outputs the robot link transforms.
And how do we get from there to the actual 2D action flow?
They use the camera extrinsics and intrinsics, basically the camera's physical position and its lens properties in the world. And they project the visible trajectories of the robot's surface straight onto the 2D image plane.
But they are super rigorous about this projection, right? They don't just blindly throw points onto the image.
No, not at all. A point's visibility is only validated if it hits 3 criteria. First, it has to have a positive camera depth. Second, it has to fall strictly within the image bounds.
And third,
it has to match the rendered depth buffer.
Okay, this is a brilliant little implementation detail because they evaluate that depth using a 3x3 pixel neighborhood, not just a single pixel.
Yeah, that's such a great engineering choice.
Anyone who's worked with robotic vision knows that silhouette boundaries, the very edges of the robot arm in the image, are just incredibly noisy.
It's so noisy. If they only checked a single pixel, they would get massive amounts of false rejections right at the edges of the robot.
Exactly. Expanding it to a 3x3 neighborhood is one of those tiny, battle-tested decisions that makes a pipeline actually robust in the real world.
It saves the system from discarding perfectly valid motion data just because of a slight rendering glitch at the edge of the frame.
So that's deployment. That's when you control the environment. But offline training is a totally different beast.
Oh, completely.
We have massive data sets of robot interactions, and the vast majority of them do not have perfect metadata.
No camera calibration, no joint logs, nothing.
So how do they handle the video-only construction mode? How are they training on this heterogeneous data?
They rely heavily on dense flow tracking. They run a flow tracker over the raw interaction videos to extract the dense image plane trajectories of literally everything moving in the scene.
But just having a mess of moving pixels isn't enough, right?
No, you have to separate the actor, like the robot or the human hand, from the environment and the objects it's manipulating.
And they used grounded masks for this.
Yeah, specifically SAM3, the segment anything model. They use it to segment the visible embodiment from the manipulated objects.
Which is amazing because it means they can extract the exact same trajectory representation for training without a single piece of geometric metadata.
Exactly.
Which is the absolute holy grail for data scaling. Any interaction video can become training data now.
But, and there's a big but here, having the language is one thing. Teaching a massive neural network not to cheat while learning it is another entirely.
The shortcut learning problem.
Right. If you just feed raw separated video flow to a causal world model, the network might just link pixel motions together statistically.
Like if the robot arm always moves exactly when the block on the table moves, the model just says, cool, these two things move together.
Yeah, it might never actually learn that the physical arm is the physical object causing the block to move.
So to combat this lack of causal understanding, the team implemented 4 distinct mask sampling conditioning modes during training. And I love this logic. Let's walk through it.
Sure. So the first is the embodiment mode. Here, the system isolates and selects only the tracks of the acting body as the primary condition.
So by showing the model only the flow of the robot arm, you force the network to predict how the rest of the static scene is going to respond to that intrusion.
Exactly. Then there's the object mode, which flips the script. It supplies only the task or the desired motion flow of the item being manipulated.
Okay, followed by the all mode, which is kind of the fallback. It shows both the actor and the object.
And finally, the none mode.
Which is basically conditioning dropout, right?
Yeah, it forces the model to rely entirely on its internal representations and the static context of the scene with 0 motion clues.
It makes me think of training an autonomous driving model. If you want the car to truly understand causality, you might selectively blur out the steering wheel in some runs, blur out the road in others, or blur out the other cars.
Right, you're intentionally blinding the model to specific variables.
It forces it to deduce the true causal relationship between the actor and the environment.
And by constantly varying which part of the flow the model is allowed to see, Hydra-0 is forced to learn that the embodiment flow mechanically causes the object flow. It actually learns the physical consequences of motion.
Okay, so we have the universal language and we know how to train it safely. Let's dive into the architecture itself, because action flow isn't just some clever hack for a custom-built model.
No, they designed it as a completely portable interface.
Right. They tested this across entirely different pre-trained video generation backbones. They used Cosmos 2.5, which is a 2 billion parameter model, and WAN 2.2, testing both the 14 billion and 5 billion parameter variants.
And let me tell you, integrating a completely new conditioning format into a massive pre-trained model without catastrophically destroying the existing weights is a very delicate operation.
So let's get into the weeds on how they did it with Cosmos 2.5. The standard Cosmos 2.5 latent space has 16 channels, right?
Yeah.
So you have this new visual action flow data.
Yeah.
How do you inject it without blowing up the model?
They form a 17-channel motion side input.
Okay, so the 16 propagated feature channels from the flow plus one more.
Right, they append one additional presence gate channel.
And the calculation for that presence gate really caught my eye. They use a Gaussian locality parameter. The paper mentions setting an inverse temperature parameter to 220. What does that actually mean for the neural net?
Conceptually, you can think of it as a super strict heat map. They calculate the weights of the top two nearest trajectories to a destination cell in the latent space.
Okay.
And by setting that inverse temperature dial all the way up to 220, which is incredibly high, they force the model to be hyper-focused on the exact specific pixels that are moving.
Ah, so it doesn't vaguely smear its attention across the whole arm or the background.
Exactly. They take the raw weight sum of those trajectories and clamp it to a strict range between 0 and 1. And that clamped value forms the presence gate. It tells the model exactly where the action is valid.
That's so clean. And then this newly constructed 17-channel side input goes through a separate zero initialized patch projection before being added to the network.
Yep, the classic control net trick.
It's so good. Zero initializing that projection layer means that at step one of training, the side input outputs all zeros and contributes absolutely nothing. The model just acts like base Cosmos 2.5.
But as the weights slowly update, it gracefully learns to incorporate the action flow condition.
It's such an incredibly stable way to inject new capabilities. They just add these embedded tokens directly to the noisy video tokens at every single denoising call.
It is an elegant architectural choice. But going back to what you said earlier about latency, building an elegant model is only half the battle. Video generation models are notoriously slow at inference.
Yeah, autoregressive generation takes forever.
And if you want this to serve as a practical world model evaluating real-time robotic actions, it has to be fast.
Which brings us to the distillation process. They used long-lived 2.0 for few-step distillation. Break down how they optimize the inference speed here.
Through distillation, they teach the student model to generate future video chunks using just 4 denoising steps.
4 steps, instead of the dozens or hundreds usually required.
Exactly. And to do this efficiently over longer horizons, they reuse the clean history through a KV cache, a key value cache. Yeah. But there's a major technical hurdle here.
Right, because when you generate video in chunked autoregressive steps, keeping the action flow temporally aligned is really hard.
It's very difficult. If the motion condition resets at every single chunk, the robot arm is just going to jerk around unpredictably.
Because it loses its temporal anchor.
Precisely. So to solve this, they slice the motion condition at absolute chunk offsets.
Oh, okay, so this ensures the continuous trajectories don't accidentally re-anchor themselves at the boundaries of every new generated chunk?
Yes, because if they didn't do this, it would completely break the physical consistency of the predicted motion. The physics simulation would basically be useless.
That is just brilliant engineering to maintain temporal stability. Okay, so we've covered the theory, the training strategy, the architecture, the speed distillation.
You know, for the fun part.
Yes, the empirical results. If you're listening, you probably just want to know the numbers. Did this actually crush the traditional baselines?
Unambiguously, yes. And by a massive margin.
Let's hear it.
The researchers ran a controlled comparison using the Cosmos 2.5 backbone, specifically to isolate the conditioning method. So they compared standard native relative 6D action conditioning against their actionable flow method.
Yeah.
A 90.4% lower robot motion error.
That is absurd. And just to clarify for everyone, when we say robot motion error here, we're talking about endpoint error, or EPE, of the gripper flow.
Right. EPE is the gold standard for this. It measures exact adherence to the commanded trajectory. It's a pixel-perfect evaluation of whether the robot in the generated video actually moved to the precise coordinates you commanded it to.
And the improvements didn't stop there, right? They cascaded down the pipeline.
Yeah, the improved physical grounding led to a 60.2% lower object motion error as well.
A 90% drop in kinematic error simply by changing the formatting of the prompt fed to the video model.
And when they evaluated across the different backbones, the distilled 1, 2.2, 14 billion parameter four-step model scored the best overall in almost every single visual metric: PSNR, SMO, FID, FED.
But okay, there is a really interesting wrinkle in the data tables that I want to highlight because I think it says a lot about the current state of AI evaluation.
VLM judge scores.
Yes, if the kinematic motion error, the EPE, is so vastly superior, why did the VLM as a judge scores show such mixed results? They used GEMMA 431B to evaluate the video outputs, and it didn't always prefer the Hydra-0 output over the baseline. What is happening there?
Oh man, that discrepancy highlights a fundamental flaw in how the industry currently evaluates physical AI.
Explain that.
Well, vision language models, like GEMMA 4, they evaluate general physical plausibility. They look for temporal consistency and object permanence. They look at a video sequence and say, yes, that looks like a realistic metallic robot moving a realistic cotton shirt without the pixels melting into a puddle.
Right, but the VLM has absolutely no idea what the underlying commanded trajectory was supposed to be.
Exactly. It is completely blind to the control inputs. The VLM doesn't know you commanded the gripper to move exactly 3.5 centimeters on a specific 3D vector.
Yeah.
It just judges whether the movement looks pretty.
And if your goal is actual robotic control, realism alone is completely insufficient.
Precision is everything. Flow EPE is the metric that actually matters for engineers because it measures mathematical adherence to the kinematics. A video that looks beautifully realistic but completely disobeys the control input is literally worse than useless for robotics.
That philosophical difference between a video looking real and being physically accurate makes perfect sense.
Yeah.
Okay, which brings us to the final and arguably the most important aspect of the paper, real-world applications.
Right, deploying it on hardware.
Beyond just predicting mathematically accurate videos, how are they using this to solve physical AI tasks?
The first major application they showed was open-loop policy evaluation. They ran Hydra-0 on the RoboLab benchmark.
So the core question here is, can this world model predict whether a specific untested robotic policy will succeed or fail at a physical task before you ever run it on expensive hardware?
Exactly. And the correlation they achieved was just ridiculous. They reported a Pearson correlation of R equals bitters 0.96 between the generated, replayed success rates from the model and the actual reference success rates on real hardware.
0.96. It's practically functioning as a perfect digital twin for evaluation.
It really is. But, and this is where it gets truly crazy, the most fascinating capability, arguably the biggest conceptual breakthrough in the entire paper, is what happens when you run this system in reverse.
Yes. They turned this forward prediction engine into an emergent world action model.
Because the interface is a shared visual language, it works bidirectionally.
Walk us through how this inverse mode actually functions, because this blew my mind.
Okay, consider a scenario where you have a simple RGB video of a human demonstration, say just a person's hands folding a piece of cloth on a table.
Just a standard video, nothing special.
Right. The system can watch that raw video and extract the desired object flow. It calculates exactly how the cloth deformed and moved through space. Then you feed that desired object flow into Hydra-0 as the condition, and it predicts the compatible robot motion required to achieve that exact same object manipulation.
So instead of predicting the future state from an action, you are predicting the necessary action from the desired future state.
Yes. And once Hydra-0 predicts the necessary visual trajectory of the robot arm, a trained, lightweight action head maps those latent visual features directly into executable, real-world joint actions for the specific target robot.
It is quite literally visual lip reading, but applied to robot mechanics.
Unbelievable.
You don't need a roboticist to sit down and meticulously program the joint angles. You don't even need task-specific expert robot demonstrations on the target hardware. You just show the system a video of what you want the object to do, and the model backward engineers the exact joint movements required by its specific embodiment to make it happen.
It completely bypasses the traditional agonizing pipelines of reward engineering and imitation learning that have bottlenecked robotics for a decade.
It's just wild.
It seamlessly connects heterogeneous internet training data, highly accurate open-loop evaluation, and zero-shot robot control, all through this one shared, pixel-aligned interface.
Because by expressing motion strictly in the coordinates of the visual observation, the model stops blindly memorizing joint angles and starts actually understanding the causal consequences of motion in 3D physical space.
Exactly. It's a true understanding of physics.
So to summarize this massive amount of ground we've covered today, Hydra-0 successfully shifts the paradigm of physical AI. We're moving away from trying to force models to memorize and reproduce task-specific, embodiment-specific joint behaviors.
Thank God.
Right. Instead, we are...
And the fact that they achieved a 90% reduction in motion error while enabling zero-shot cross-embodiment control, I mean, it proves that visual action flow is likely the missing link we've been searching for to enable true generalist robotics.
It absolutely does, which leaves us with a pretty wild final thought for you to consider today. If a generative video model like Hydra-0 can extract perfect inverse kinematics simply by watching how a piece of cloth deforms in a human's hand, do we even need complex, manually engineered physics simulators in the long term?
That's the big question.
Right. Or will the video generation model itself inevitably become the ultimate universal physics engine for literally any physical embodiment we can possibly imagine? It challenges the entire foundation of how we currently build robotics.
It really makes you rethink the whole stack.
Something to mull over while your training runs finish. Thank you for joining us for this deep dive into the source material. Keep building.